Hello and welcome to this lecture. We are going to start looking at adjoint of a linear map, and this starts a new week in this course as well, week 9. So let's get started by looking at it. This word adjoint, if you looked at determinants and all that before, there's the same word adjoint is used for something else, another matrix. We will not use that as far as this course is concerned. So for us, adjoint will be what I'm going to define in this lecture. Okay, so keep that in mind. Okay, a quick recap. We've been looking at vector spaces over a real or complex field. We saw how linear maps are very important to understand what goes on in vector spaces, and linear maps have this nice fundamental theorem. There is a matrix representation and 4 fundamental subspaces for a matrix. In particular, these invariant one-dimensional subspaces, eigenvectors and eigenspaces and eigenvalues are very important to understand linear maps particularly well. Diagonalizable linear maps are easy to deal with, and we saw how inner products and norms and this notion of orthogonality helps us tremendously to simplify things in understanding linear maps. So in particular, we saw in the last few lectures orthogonal projection, which gives you the closest vector in a subspace, and it's associated with this least square solutions for linear equations, and both of these are very good applications even in learning and very recent topics of interest. Okay, so this is a quick recap of where we are in this course, and from now on we are going to study operators in inner product spaces. Okay, so we have these inner product spaces, and what are the special type of properties that we can give operators in inner product space. Look at the effect of how operators affect inner product. Okay, so that's sort of the way in which we will look at it. So you can think of how it will work. For instance, you have two vectors u and v, and you have an operator. There is an inner product between these uv, and then after you have operated with the t, they go to some other domain, and you can also do an inner product there. So are there connections between these inner products? Are there some interesting things we can do around these inner products is the central question here, and there is a nice study of that we can do, and these adjoints are very important in that study. Okay, so when the properties of the adjoint of an operator will tell you a lot about the operator itself. Okay, so that's where we are going, okay, from a high level. So let's get started. Okay, so let's recall one connection between linear functionals and inner product that we saw. So now we're going to study how linear maps affect inner products, or how inner products shed light on linear maps. Both ways we will look at it now, beginning with this lecture. But before that, we've already seen one nice little property, particularly with respect to linear functionals, right? So if you have a vector space, I will take a finite dimensional vector space because this result holds in that. And if you have a linear functional from the vector space to the scalar field f, then we have this raised representation theorem, which says there's a unique u such that this phi of v is given by the inner product of v comma u. So all linear functionals are inner products with some chosen vector, one vector. There's nothing else that is a linear functional. So when you have one dimension, there's this nice property. And how do you find this u? If you have to find this u, we use this orthonormal basis. If you take an orthonormal basis and simply apply phi on each of these things, and then just reorder and use the properties of the inner product. Because when you in an orthonormal basis, the coordinates, you can write any vector u, any vector v as inner product v comma e1 plus so on, and then you just use the properties of the inner product, take the phi inside, etc., and then you will get this answer. So there is a very direct and simple way to compute this unique vector u given the linear function. Okay, so this is the background, and we will use this in a very nice way to study inner products and linear maps. Okay, so for that we will first look at extracting some interesting linear functionals from a linear map. Okay, so a linear map is given to you. I'm going to think of a linear map now from a vector space v to another vector space w. Okay, both are finite dimensional inner product spaces. So this is the new thing. So far we have not brought in the inner product. I'm going to now bring in the inner product. Okay, so there is, both of them are inner product spaces over the same field f. Okay, and then t from v to w is a linear map. Okay, so this is our setting. We will fix some w, small w, in the range space as in capital W. Okay, we'll pick one vector W there, and then I will define this linear functional from V to F, which is defined as mentioned here. So, you take the inner product of TV. Okay, so TV, if you take a V in small v, which is a vector in capital V, you apply T to it, you go to W, and I already have this other small w sitting there. I take an inner product of those two, I get a number. Okay, so it's almost as if this this phi t comma w captures what part of w is in t in some sense, right. So t takes any vector v to tv, and then what is the connection between that and w? You're taking that inner product to figure that out. So that's the functional. Okay, so the functional itself has a very simple definition. It's not wrong to define this. Now, what does Rees say in this picture? In this picture, using the Rees representation theorem, you know that there is a unique u in V such that this linear functional inner product Tv comma w is always equal to V comma u T w. Okay. So, at this point, let me draw a picture to illustrate what is going on. This will help you maybe picture this. So, you have V and you have W, and there is this small w that I have identified, okay, and you have a V which takes you by T to T times V. Okay. There is an inner product that you can do between these two. Okay, you will get a linear functional. Now, once I fix a w and this linear functional is well defined, I know that there is some u t comma w in V, right, and this inner product and this inner product have to match, isn't it? So, that is what Rees representation theorem is telling you. So, you pick some w, right, you pick some w, and there is this t given to you, and you define this linear functional using just w and tv. You know by Rees representation theorem that there is a u t comma w, and anytime you do this or you do the direct inner product with v and w, you should get the exact same answer. That is what Rees representation theorem is telling you, isn't it? So, this picture I think is a good picture to remember, and you can also see we are taking our first steps towards mixing up inner products and linear maps, right. So, how do you mix inner products and linear maps? As in mixing in the sense, how do you study the effect of a linear map on inner products, or how do you study how inner products shed light on linear maps, right. So, these are the sort of ideas you can do. So, you have inner product before the linear map, inner product after the linear map, and there is this connection between the two, right. So, you take linear map and then evaluate inner product with a fixed vector w. It is the same as doing an inner product before. Okay. So, the inner products through linear maps are preserved in some interesting fashion in this way. Okay. So, this is the Rees representation theorem. So, let us see an example, a concrete example. You will see how easy this is. I mean, this sounds like a very abstract idea, but when you break it down to a concrete example, particularly in finite dimensional Euclidean spaces, this idea is very, very simple. Okay. Here is the illustration. Okay. So, let us take R4, and this x is a vector in R4, and let us look at a very simple linear operator Tx, which is what I have defined here. It is one of my favorite operators. If you want, you can write down matrix here. So, this matrix representation of T is 1, 2, 3, 4, 3, 4, 5, 6. I have used examples of this sort throughout this course, so maybe there is some familiarity with it. This is the matrix representation. So, Tx just simply goes to this. If you pick the standard basis, for instance, you will get this. Okay. So, that is T for you, a very simple operator. So, now suppose W is 1 comma 2, right. So, you remember T goes from R4 to R2, and I have picked one particular vector 1 comma 2 in R2, and then I am going to look at Tx comma W, right, the inner product of Tx and W. So, 1 comma 2 inner product with this is going to be simply this, right. It is a specific expression and it belongs to the real numbers, right. So, it belongs to R. So, this is just 1 times this plus 2 times this. So, it's a very simple expression. I hope I have not made any mistakes here. Yeah, so it looks okay to me. Okay, so it's just 2 times the second coordinate plus 1 times the first coordinate. That is Tx comma w, and clearly I didn't mention it here, it does belong to R, right. So, it is a linear functional Tx comma w, right. Isn't it? Now, from this you can quickly read out what ut comma w will be, right. See, if I have to write Tx comma w as a utw comma v, this is what it is, right. So, this guy is equal to inner product x1, x2, x3, x4 comma this u, right. This u is 7, 10, 13, 16, isn't it? For any x, it is true that Tx comma w is simply an inner product of that x with 7, 10, 13, 16, and this is all that race representation theorem is saying. Okay, so, when you take a simple example, it is a very easy and rudimentary thing to see. Okay, so, Tx comma w, there is always a u. Once you fix the w, there is always a u, a fixed unique u, such that Tx comma w becomes an inner product with this. Okay, it is as simple as that. Okay. What if you make this w as an arbitrary w1, w2? Okay. I took a particular example here 1 comma 2, maybe you do not like this example 1 comma 2, maybe it is not good enough for you, it is not clear enough for you. You take an arbitrary w1, w2. Now, what happens when you do Tx comma w? You can go back and plug in w1 times the first coordinate plus w2 times the second coordinate and simplify, and you will get this. Do you get this? So, now this is also an inner product of utw and x, right, and you can pull that out here. See, these coefficients come out, w1 plus 3w2, 2w1 plus 4w2, 3w1 plus 5w2, 4w1 plus 6w2. So, for an arbitrary w in R2, okay, for an arbitrary w in R2, utw is a linear map into R4. Is that okay? Okay. Do you see how this worked out? For an arbitrary w, this thing of finding utw. So, now you want what is utw, you write it out and identify utw, and if you look at the map from w to utw, this map is a linear map, isn't it? This is just a map, I mean a map from w to utw, and that ends up being a linear map from R2 to R4. Okay, once again backtrack, you have a map, a linear map from R4 to R2, and you have found a linear map from R2 to R4 which sort of captures your inner product Tx comma w. Is that okay? So, this gives you a very clean and nice example, and this example is good to keep in mind as you go through the rest of the theory, which defines adjoint and all that. It is a very simple definition at some level, but when you do it in theory, sometimes it looks like I am pulling out all sorts of notation and terms, and this picture, this little example here should help you clarify what is it that we are actually talking about, right. So, there is this nice linear map which we seem to have discovered from R2 to R4 in a very interesting and simple way, and the adjoint simply is a generalization of this example. Okay. So, let us see that. Here is the definition for the adjoint of a linear map. We have two vector spaces V and W, both finite dimensional inner product spaces over a field F, and we have a linear map from V to W. Okay. The adjoint, okay, so if you pick a W, a small w and capital W, using race, we know that there exists a unique UTW in V such that this inner product TV comma W equals V comma UTW. So, this U we know is unique, and this comes from the race representation theorem. So, this is left hand side as a linear functional, right hand side has to be an inner product, and this U will have to be unique. Okay. So, this is what we know already, in the adjoint of T, which we will denote as T star. Okay. In this course, we will use the notation T star for the adjoint, is that function from W to V which maps W, small w, to ut comma W. Okay, so we saw in the previous example how this map ended up being a linear map as well. We will show it's linear soon enough, but this is the definition. At this point, I am defining that adjoint as simply a function from W to V, which maps W to UTW. Okay. Now notice this is a very important property, and we will use it again and again and again to make our understanding of linear maps very clear. Okay. TV comma W, the inner product between TV and W is the same as the inner product between V and T star W. Okay. So notice this T star W is my new notation for UTW, whatever I had as UTW. Is T star W, my new definition of adjoint, and it satisfies this wonderful relationship. Once again, a picture. I have drawn this picture before too, but it's good to draw this once again now that we have an adjoint and all that. So you have V and you have W, and you have a V that takes you to by T to TV, and you have any W here, you would have the adjoint which takes you to T star W. And what is so great about T and T star? They preserve this product. The inner product between TV and W in W is equal to the inner product between V and T star W in V. Okay. So this is sort of the abstract generalization of the previous example that we saw in defining T and T star, and this adjoint exists in this fashion. Okay. So later on when you do advanced courses, people would generalize this to other types of spaces and all that, and the adjoint mapping in philosophy will work in the same way. Okay. So this is the definition of an adjoint. Okay. And we saw in the previous example that the adjoint ended up being a linear map in that case, and that is in general true. So that is what we will prove next, and let's see, before we go there, let's revisit that example and make sure we understand exactly what it is. And we see that W is in W1, W2, and you look at this inner product and you read off T star W as this map. Okay, so you can see T star W is a linear map. Both of these are linear maps. One takes you from V to W, another one takes you from W to V, and they are both given by, in a very simple way, they are given in this fashion. Okay. So in fact, there is matrix representation for these things, and later on we will look at matrix representations. At this point, I will simply stop with the definition of adjoint. Okay, so the general property that one can quite easily prove is that adjoint is a linear map. Okay, so if you take any finite dimensional vector spaces V and W, and T is a mapping from V to W, T star is the adjoint of T, and that is a linear map from W to V. Okay, the proof is not very hard, it just involves that same property. If you were to look at the adjoint of W1 plus W2, you can show it is adjoint of W1 plus adjoint of W2. Okay. So how do you prove that? So if you look at V comma T star of W1 plus W2, so this is the property, and this is equal to TV comma W1 plus W2. You use that same property again and again. But once you come into this world, this will split. This is distributive, right? W1 plus W2. So you write like that. And then each of these things is, again, you go back to the adjoint, and then you again use the distributive property. You get V comma this. Okay. Now you know that this T star W is unique in some sense, right? So this and this have to be the same. So T star of W1 plus W2 equals this. Okay. So that's what this means. Same proof you can do for T star of AW. Okay. You do the same thing. There will be some conjugation going back, forth, etc., and you will get this. So what these two things prove is that T star of W1 plus W2 equals T star W1 plus T star W2, and T star of AW equals A times T star of W. So these two things together show you that T star is a linear map. So this is a way to prove this result. So what we have done in this short lecture is defined adjoint for a linear map as something that maps the inner product from one part as the inner product in the other way using this linear functionals argument and Rees representation theorem. We know that this adjoint is a map from W to V, like if T is a map from V to W, T star is a map from W to V, and T and T star seem to be intermingled and they are connected wonderfully by this inner product in both of these spaces. Okay. So this is a general linear map. When we specialize to adjoint of an operator, you will see many more interesting things will come. But even in this case, there is a nice little way to define various things around T and T star. So you'll see a lot of interesting ideas can be developed around that. Okay, this is the end of this lecture. We'll take it up, take up more interesting properties of adjoint and study it further in the next one. Thank you very much.